Before any military aircraft ever sees a drawing board, pilots and engineers must use their knowledge and instincts to look into the future. They must estimate the technological advances that this aircraft will face and then develop the requirements. From these individuals came the objective: to design and build one aircraft to be a single-seat, twin-mission strike fighter for use aboard aircraft carriers or ashore. To have the performance, agility, and weapon systems to perform any mission now and in the future. A multi-mission aircraft in any weather and around the clock and around the world. The aircraft must be versatile enough to land at a semi-prepared remote landing strip with little or no support equipment, or to be serviced on a pitching carrier deck far out at sea, to be a highly reliable and easily maintained aircraft serving the U.S. Navy, Marine Corps, and America's allies into the 21st century. All this capability in one airframe? It used to be called impossible. Today, it's called the FA-18, the Hornet. The Hornet is the result of operating on the leading edges of technology in aerodynamics, electronics, and computers, all wrapped in sheets of the most advanced metals and composite materials known. The Hornet drop test program was an example of the exhaustive testing which assured that what went up could come down safely. These efforts made the Hornet one of the most sophisticated and effective weapons systems in the free world. After more than 3 years of development work, the FA-18 began full-scale development testing, beginning in 1979 at the Naval Air Test Center at Patuxent River, Maryland. Any modern flight test program has one major criteria: get the best possible aircraft at the lowest possible price. The success of any flight test program is measured by the efficiency of the program and its ability to meet schedules. By the end of 1980, 10 full-scale development Hornets and 4 pilot production Hornets were taking part in the test program. Not only were the aircraft systems tested, but the Hornet's ability to be a weapon system itself were put through the paces, with the test pilot coaxing all the available data he could out of the aircraft. The enormous volume of electronic data being absorbed by the test team on the ground is being supplemented by a continual patter from the pilot to try and help the test team experience the flight. Spin testing and in-flight arrestor cable landings were just 2 of the hundreds of flight tests carried out during the program. Advanced aerodynamic research led to the Hornet's wing design. This design has leading-edge extensions which greatly improve the high angle of attack characteristics of the aircraft and the performance of its engines. In early 1982, the FA-18 made its first fully automated hands-off landing at the Naval Air Test Center. The test was performed to demonstrate the Hornet's suitability for carrier operations, including the FA-18's compatibility with the fleet's automatic carrier landing system. This system and the approach power compensator aboard the Hornet are in full command of the aircraft's flight controls and throttles during approach and landing. At a pre-designated point, several miles from the landing threshold, the Hornet pilot couples his radar to the radar on board the carrier. The radar transmits a signal to guide the aircraft onto the carrier's pitching deck. McDonnell Douglas Corporation was initially the prime contractor, and Northrop was the major airframe contractor of the initial Hornets. Supporting that group are hundreds of subcontractors across the United States and abroad, manufacturing an aircraft that is, by weight, 55% aluminum, 14% steel, and about 10% is graphic composites and just over 8% titanium. The General Electric 404 low-bypass engine was designed especially for the Hornet and is truly an outstanding performer. The GE 404 is in the same thrust class as the renowned J79 engine which powered the F4 Phantom, and yet the 404 is smaller, more compact, and weighs half as much. The Hornet's twin engines generate 32,000 pounds of thrust in afterburner, a thrust greater than its own total fighting weight, giving the aircraft the ability to accelerate while climbing straight up. These engines are efficient, lightweight, and simple, reflecting the Hornet emphasis on increased performance and simpler design. And two 404 engines consume only 10 to 15% more fuel than other single-engine aircraft the Hornet replaced. The Hornet is an airborne arsenal. It can carry 18,000 pounds of weapons in the attack mission. Hornet designers insisted on an airplane able to win the beyond visual range engagement using its radar and radar-guided missiles. An airplane equally capable in the close-range dogfights with Sidewinder missiles and cannon, and an aircraft able to win at very high speed or very low speed. Even in bad weather, multiple targets that are beyond the pilot's visual range can be attacked and destroyed simultaneously. Rounding off the Hornet's weapon system is an internal 20mm Vulcan cannon, firing at a rate of up to 6,000 rounds per minute. The Hornet was designed from the beginning to fulfill dual missions. It was designed as a superior air-to-air fighter and deadly air-to-surface attack aircraft. It now not only fulfills both missions extremely well, but it excels at them. The reason for this is the heart of the Hornet, the major factor that makes it so unique and versatile, its futuristic cockpit. Human engineering specialists have designed a multi-mission crew station right out of Star Wars. The pilot is at the center of a computer-driven information center. Gone are most of the dials, knobs, and toggle switches of yesterday's aircraft. These have been replaced by two computers connected to three cathode ray tubes. Due to limited space, the cockpit has been arranged to minimize the amount of action required to manage this entire weapon system. All of the pilot's tasks have been divided into three main areas. First, control and monitoring of all aircraft systems. Secondly, the management of communications, navigation, and identification systems. And thirdly, the radar sensors and weapons. Each of these is centralized on one display in front of the pilot's eyes. Surrounding the CRTs are 20 push-button optional mode controls which can call up and display any required data. It is well known that the requirements for an air-to-air radar are definitely different than those for an air-to-surface radar. One of the major reasons why the Hornet is so versatile is the all-digital, multi-mission radar designed and built by Hughes Aircraft. It is a marvel in its own right with unparalleled flexibility in a wide range of operating modes. The radar's high-speed signal processor can sort through data at lightning speed, giving a clearer radar picture. Let's look at this radar in the air combat scenario. In the long-range velocity search function, the radar scans the sky ahead of the Hornet, concentrating on contacts that are approaching and providing data on the direction of the threat and its closure speed. Raid assessment is also available to determine the number of any attacking aircraft. This information provides an advantage to the Hornet pilot prior to entering the dogfight. The track while scan format allows the radar to assess up to 10 targets at the same time. It also notifies the Hornet pilot which target presents the greatest threat to his aircraft. The pilot can then lock on to any single target for his missile launch. The steady shoot cue is displayed while inside the maximum range of your selected missile, and a flashing shoot cue is displayed when the highest percentage chance of a kill is possible. A radar warning system will alert the pilot if he is being tracked by another radar, and flare and chaff dispensers can be used to counter ground-to-air or air-to-air threats. During intense air combat maneuvering, the pilot must be able to keep his target in sight without taking his hands off the stick and throttles. Engineers have recognized this need by locating all time-critical controls for the air-to-air and air-to-surface attack on the control stick and the throttle. Capping the versatility of the cockpit is a heads-up display, which is the primary status display. Positioned in the pilot's forward field of view is displayed such information as airspeed, attitude, angle of attack, altitude, heading, Mach number, G-loading, and destination heading. This information is also used for the delivery of weapons, while onboard computers take into consideration delivery mode, aircraft dive angle, airspeed, and a multitude of other factors to produce pinpoint accuracy. The accuracy of the Hornet weapon system provides a high probability of a first-pass target kill, and combined with the Hornet's high speed and rapid acceleration, it will mean a minimum amount of time spent in the target area. In keeping with its advanced design, the Hornet has a fly-by-wire system. What this means simply is that all flight control surfaces are controlled by digital signals from the onboard computers. The surfaces are no longer dependent on rods, wires, and pulleys to move. As the pilot moves his stick, sensors feel this motion and convert it to electrical signals, which position the appropriate actuators and their respective control surfaces. Operational capabilities of all fighter aircraft are dictated by the amount of fuel which can be carried on board. Fuel is carried in 4 interconnected fuselage tanks and 2 internal wing tanks. Fuel can also be carried in 300-gallon external tanks on wing pylons or on the center line of the fuselage. The ferry range of the Hornet is approximately 1,600 nautical miles. The Hornet is also equipped with an in-flight refueling system capable of receiving fuel from most airborne tankers. With the ability to carry over 16,000 pounds of fuel, the Hornet has a fighter escort range exceeding 400 nautical miles, plus time for air combat maneuvering, and its air-to-surface radius is better than 500 nautical miles. After a mission, back at the base, the ground crew can go to one spot and examine one panel and get a detailed indication of what has failed and where. This panel, called the Maintenance Monitor Panel, also indicates whether or not any of the onboard consumables will need servicing. Problems can be quickly located, isolated, and the offending components replaced when necessary. The Hornet was designed to spend minimum time on the ground and maximum time in the air where it does its work. The excellence of Hornet performance, rapid acceleration, high speed, turn rate, and climb make the Hornet a peacekeeping tool of awesome proportions. The Hornet anticipates the development of new, perhaps superior weapon systems and provides for their employment. The Hornet is truly an impressive fighting machine. It can fly at nearly twice the speed of sound and can reach up to 10 miles into the sky. It can endure stresses nearly 7 times the force of gravity, and yet it can fly at speeds so slow that most other fighter aircraft would stall. For survivability, the aircraft has multi-backup systems in its flight controls and avionics, and along with 2 engines, permits mission completion and get-home capability. Prior to operational deployment to the U.S. Navy evaluation squadrons, VX-4 and VX-5 completed an extensive evaluation of the Hornet's capabilities in the fighter and attack roles. During the evaluation period, the squadrons flew the Hornet for more than 1,600 flying hours. This program was conducted at many of the U.S. Navy's test facilities throughout the country. In a 2-week deployment to Naval Air Station Fallon, Nevada, 11 Hornet aircraft flew 130 missions in 280 flight hours. An important part of the FA-18 evaluation, just as important as its fighter attack capabilities, is its compatibility within the aircraft carrier environment and its reliability at sea. In August of 1982, sea trials for the Hornet were conducted aboard the USS Kennedy as it operated off the Virginia coast. During September of that year, VX-4 and VX-5 also flew off the USS Constellation during those squadrons' operational evaluation. They were joined by representatives from VFA-125 who flew from their home base in Lemoore, California to the carrier operating off the California coast. Along with launch and recovery capabilities, sea trials were needed to determine the Hornet's deck handling characteristics, as well as the aircraft's reliability and availability. Deck crew handling was demonstrated through a series of tests such as aircraft tie-down at various spots on the flight deck and operations on the elevator with other aircraft. Through the sea trials, the Hornet demonstrated 100% aircraft availability, allowing the testing to be carried out uninterrupted. This evaluation concluded the longest aircraft assessment in U.S. naval history. VFA-113 went aboard to become the U.S. Navy's first operational Hornet squadron in 1983. Some 40 squadrons became operational for the U.S. Navy and Marine Corps from the 1,377 aircraft initially ordered from McDonnell Douglas. The first Hornet squadron, VFA-125, the Rough Riders, was officially formed on the 13th of November 1980 at the Naval Air Station Lemoore, California. The mission of VFA-125 as a replacement training squadron is to train new Hornet pilots and maintenance personnel for the fleet squadrons. Initially, however, VFA-125 was tasked with the training of the first Hornet instructor pilots and support personnel. Inside a 40-foot dome resembling a planetarium, the Air Combat Maneuvering Visual System allows realistic, cost-effective air-to-air and air-to-ground combat training for Hornet pilots. Air combat maneuvering is the pinnacle of flying performance. It combines every basic flying skill at the level of maximum performance where indecision or error can mean death. The imagination and concentration that allows a fighter pilot to maneuver confidently in the three-dimensional arena are a product of hard work and attention to detail. Inside a cockpit that duplicates a Hornet's own sophisticated controls and electronic displays, the student experiences all the sights, sounds, and other sensations of combat. The heart of the simulator is a high-speed computer which controls several projectors that throw fast-moving images of Earth, sky, planes, and even incoming missiles onto a screen. Although the pilot is stationary, he has the illusion that he is flying. To complete the illusion, as he manipulates controls to bank, the computer tilts the horizon. When the pilot closes in on his target, the image automatically enlarges and the pressure on his G-suit increases. Using the simulator, a pilot can complete 30 air-to-air or air-to-ground mock attacks in an hour instead of the 3 possible in a real jet. The training syllabus for Hornet pilots will include 200 hours of academic training and 85 hours of familiarization with the FA-18 and its systems. Included in these 85 hours are 63 hours devoted to air-to-air and air-to-ground training. This makes the Hornet pilots dual qualified. Qualifying to fly off aircraft carriers will require an additional 22 hours. One of the innovations in the training program is computer-assisted ground school. Students will learn much of their background in technical material in computer terminals. Hands-on throttle and stick, or HOTAS trainers as they are referred to, permit ground instruction of cockpit displays in switchology and reduces expensive air training time. Foreign sales, an important consideration in any new aircraft development program, is an important element in the ongoing Hornet program. Canada became the first foreign country to purchase the FA-18. The Canadian government began a new fighter aircraft competition in 1975 with 5 aircraft companies submitting proposals. And after an extensive elimination, the CF-16 and the CF-18 were selected as the final contenders. Following a period of intense review and contract negotiation, on April 10, 1980, the CF-18 was selected to be the Canadian Forces' new fighter aircraft. This decision, worth an estimated 4 billion Canadian dollars, called for the delivery of the first of 138 Hornets in late 1982. Delivery of the remaining CF-18s continued through late 1988. One interesting aspect of the CF-18 is the distinctive false cockpit painted on the underside of the fuselage. This is intended to confuse dogfight opponents as to the CF-18's true orientation during air combat. There are only 2 principal differences between the basic FA-18 and the CF-18 for Canada. The Canadian Hornet will use different avionics for its instrument landing system in place of the system used by the U.S. Navy for operations aboard aircraft carriers. Also, as you can see, the CF-18s have a spotlight mounted on the left side of the fuselage for night identification of intercepted aircraft. The 2-seat version of the Hornet you see here was under consideration from the beginning. It has the same overall dimensions as the single-seat Hornet. Installing the second seat and a full second cockpit required reducing the internal fuel capacity in the Hornet by about 6%. It is also designed to be fully combat capable, allowing the FA-18B, as it is designated, to be switched from training duties to combat strike or fighter missions with the same efficiency as the single-seat Hornet. The CF-18 was procured to perform essential military missions for the defense of North America and NATO. Aircraft based in Canada are to provide air defense of North America and its adjacent maritime zones. And working in conjunction with an intensive radar surveillance network, CF-18s will intercept unidentified aircraft and intruders and ensure Canadian national sovereignty. Today, the air arms of 7 other foreign countries fly the Hornet as their first line of defense.
Very capable in both the air-to-air and the ground attack role. As you know, we've got a large country, and we're looking for an aircraft that we can deploy to airfields with little support facilities and generally under very primitive conditions. And I think for those reasons, this aircraft will serve us very well.
You